Hi everyone, this is Chia Ping here. First of all, thank you so much for being patient for my absence for the two classes. If you look back at the previous class that we have stopped, we actually discussed part of lecture 2, number systems and codes, but I thought that since I'm going to record the lecture, it's better to just start all over again. So feel free to look at it, and if there's anything that you think that we have gone through and you understood, then you can always just skip it and go to the next one. All right, so this is lecture 2, number systems and codes. Okay, so if you just recall back of whatever that we have learned, so far we have learned all these things on digital circuits, and usually it's just on either logic 0, logic 1, right? Remember, for logic digital system, usually it goes by binary bits. So binary basically means that it's a representation of whether it's 0 or 1. So by default, usually if something is off, we call it logic 0. When something is on, we call it as logic 1. So that's just how it goes usually. All right, so this is just a representation of how it would be. All right, for things that should be active during the time, we set it as logic 1 and 0 for the one that's not. Okay, so this is a representation of how things could look like. All right, when we have binary bits, basically binary bits are all the information or the signals that you need to have, basically comprising 0 and 1. All right, so what happens is that this information will go through your logic gates. Logic gates, remember the one in lecture 1 that we have learned, could be a combination of AND gates, OR gates, and whatnot. And these logic gates usually make up a point to be in a system called the integrated circuits. Basically, in short, we call it as IC. All right, and where do you see all these things? We see in microprocessors, microcontrollers, sensors, basically everything that you have had in your hand nowadays, your PC, your computer, smartphones, and things like that. All right, so remember we talked a little bit about digital and analog. All right, so always remember, for digital, usually what happens is that this is the key word here, which is called the discrete. All right, you represent the information basically on discrete voltage levels or discrete level. All right, here it could be anything. It doesn't have to be just voltage, can be current as well. All right, so it really depends on what you're trying to represent. So in this case, we take voltage for example. Discrete just basically means that it's like in short of pulse, just like you see over here in the graph. All right, so these are what we call as discrete. All right, it goes on a pulse of signals. All right, so if it's 2 levels, again, like we said, either 0 or 1, we use it as the binary information. All right, so in this case, it really depends on what kind of signal you try to fit in. And usually for digital, it always goes by 0 and 1, just like what we have discussed before, remember? So always remember, for digital, it's always in discrete signal, we call it. All right, it basically means that it's in pulse. All right, and on the other hand, all right, if you look at it, that you have electronic circuits processing information. All right, I think there's some information here that you can definitely read on your own. I want to emphasize on this analog part here. All right, what sets it different from digital is that for the information expressed here, this is the term we use, continuous. Basically means that at any given point of time, all right, your information is expressed with against time. And if you notice that instead of the pulses of signal that you see for digital, this is actually continuous. Basically means that it's just ongoing all the time. All right, so the simplest example that we could share is always, take another voltage signal. This is like a sine wave here. All right, that's why it's just represented as A sine omega t plus phi. So obviously you know that this A here actually indicates the amplitude. All right, and this is if there is any phase difference to it and all that. But most importantly, as long as you know what is the difference between digital and analog. Digital, pulse of signals, keyword is discrete, all right? For analog, it's continuous, all right? Just like what you see over here. So that's one here. This is something that we have talked about before. Logic 1 for true, false, or on or off, things like that. This is just an example of what it can be used for, all right? For example, like elevator controller. We always have it controlled by electronic logic, all right? So things on shutting the window and the sensor, and it has to give out certain volts when it's shut or give out certain volts when it's open, all right? That's one of the application. I think these are some of the things that we don't have to really go through very much in detail, but that's just really for you to know, because in the beginning what we used to have are valves, relays, and switches, all right? But whatever that we use now, it's definitely much smaller, much compact, but at the same time we have more stuff in it, all right? Fast, more reliable, and so on. Okay, so this is just an example of how it looks like as compared to how it used to be last time for things like relay. Relay is something like we usually use in terms of switch, for example, all right? You want something to be switched on or switched off and all that, and more often than not, we do use relay as part of it, all right? But at the same time, we now do have something like that moves even faster in nanopicoseconds as compared to milliseconds. So you see the difference that we have come about. All right, so okay, so now let's look at our number system and codes. Remember of what we have talked about earlier. We have binary, which is of base 2, octal, base 8, decimal, which is whatever that we have always been talking about in our daily life, all right, that's base 10, hexadecimal, all right, hexa here basically 6, all right, indicates 6 decimal 10, so it makes it up to 16. If you realize, binary is represented by 0 and 1. Octal, if you notice, right, look at the number, all right, it starts from 0 all the way to 7, all right, of base 8. What about decimal? Decimal is 0 to 9. Do you realize something? There's always kind of 1 below the base is, all right? For hexadecimal, everything is exactly like decimal up until here, because we do have 10, but after that 10 is actually represented as A in hexadecimal, and then you just proceed. This is 11, 12, 13, 14, 15, all the way up until F. So that's how it is. Remember, we have actually learned about doing the conversion between decimal to binary, binary to decimal, and so on. So as long as you're familiar with one part of it, it's the same, and every method works exactly the same, even for the different bases like octal, decimal, hexadecimal, which is something that we'll look at, all right? So this is the how we actually place the weightage of it, all right? Always remember, I think in the class we have done this before. 2 power of 0, 2 power of 1, 2 power of 2. We always start with 2 power of 0, but that's for binary, right? So if it's octal, you just replace it with 8. Hexadecimal, remember, 16, so 16 power of 0. Decimal, this is the simplest one, which is 10, all right? Just a table for you to look at, all right? So 259 in decimal. This is pretty much straightforward. I think I do not have to go through so much with you over here. All right, make it a point for you, especially in this topic here, to indicate the base of whatever number that you have written. All right, maybe for 10 and all, we get a little bit lenient about it, but make it a good habit, all right, to just indicate what base number it is, because this is so important, especially for base 2, base 8, and base 16. Okay, so let's start with the binary number system. Okay, so for binary system, we have it as base 2, so which means we only have 0 or 1. Remember, just like what we have seen earlier. So this is the example, which is 100